In this problem, we get to evaluate the effective spring coefficient, spring rate, spring constant for a network of bars or springs. And what we see here is that there are four bars acting in parallel at the top of this system, then a rigid beam, then two bars acting in parallel at this portion of the system, and then a rigid beam, and then another bar. Okay, and we have spring constants K1, K2, and then K1 again for these four bars. So let's go ahead and start from the bottom of the system where we have this applied force, and we're interested in the delta displacement here. So when we do that, we say, here is a force, here's the delta, exactly like we have here, and we draw in a spring with spring rate K1 as we see here. Now this portion is a rigid beam, so it has no deflection associated with it, and so we're going to call it a node. Now we look at the K2 and the K2 acting in parallel here, and we know that springs in parallel have an effective spring rate that is just the summation of the individual spring rates. So it becomes 2K2. Now we move up to this location, we're going to have another node, and we're going to have the combination of these four springs in parallel. So we add the spring rates to each other, and we get that it's 4K1 at this location. At the top, we can draw a force that's equal and opposite to this force, or we can think of it as having a fixed constraint. After all, the displacement that we're interested in understanding is given by this delta relative to this part here that is fixed. So at this point, we can go ahead and perform some algebra based on the fact that we have three springs in series with each other. So for that, we know that the inverse of the overall spring coefficient will be equal to the sum of the inverses of the individual spring coefficients, like you see here. So when we do some of the algebra, what we get is the following by saying, okay, we have 4 over 4K1, and we can add this and that term together. This term stays the same, and we do a little bit more algebra and simplification by adding these, putting them over the same denominator and putting these in the numerator. And the effective spring coefficient we get by flipping this whole fraction, and we have the following. So we've now got a symbolic representation of the result. I'd like to go ahead and show you how to do these symbolic manipulations in Python and also be able to provide a numeric evaluation in Python. So let's go to our Google Drive and we open up a new Colab notebook, and we're going to once again use NumPy, and we're also going to introduce not SciPy, but SymPy, the use of a library that handles symbolic parameters in Python. So to bring in the symbols that we want to use, we can call them K1, K2, and oh, you see it already knows what I want to do. We SP, so this is the SP, so it's using the SymPy library dot symbols, and then it brings them in. We can then, let's see, we can, yeah, that'll work. Okay, we can look at the algebra we've done here, and we'll call this inverse K effective. All right, maybe I'll do like that just so it's a little more visible. And we can go ahead and do 1 over K1 plus 1 divided by 2 times K2, right? We do need these parentheses in order to make sure the algebraic order of operations is preserved. And so we now have this expression, which is the inverse. We can say that the K effective will be 1 over, oh, it remembers me, like this. And if we run this, we may not see anything. So we can do a couple of things. We can print the K effective like this. And the symbolic representation is not like what we got here. So there's kind of a catch-all, try it and see if it works function in SymPy called simplify. And when we run this, we get the same symbolic result. So that's kind of fun and useful. Now, what if we want to perform a numeric substitution for the values of K1 and K2 that we have? So we have K1 is equal to 10 kilonewtons per millimeter and K2 is equal to 4 kilonewtons per millimeter. Well, there's a way to do the evaluation directly in SymPy, this numeric evaluation, and you can do this. There are multiple ways to do it, but subs and eval_f if you want. But given that we've been using NumPy and printing our results using np.round, why don't we go ahead and describe how to perform this numeric operation such that it gives us parameters, floating parameters in NumPy. So for this, what we'll do is we're going to use something called lambdafy, and we'll say that we're going to get a NumPy result. That's just to help us understand what we're going to do, and or actually let's call it NumPy function. There we go, NumPy function, and we're going to lambdafy or make a function essentially. Oh, it remembers where we first put in our K1, K2 in brackets, and then comma. What is our function that we've been using? And it's trying to be super helpful, but it's not. We have K effective. Okay, so that's what we evaluated previously. And then what we can do is plug in the values that we have. So K1 is going to be 10 and K2 is going to be 4. So for that, what we do is MP numeric value, or I could have done like MP whatever, I could have called it something else, but we're going to call our NumPy, oh, it knows, pi function, and the first one is K1, so that was the 10, and the second one was K2, that's the 4, and we can run this, and it doesn't give us anything. So now we go back to our way of saying, oh, you know, what's the K effective numerically? And we do MP round, and we do MP numeric value. Yes, okay, fine. I can't see though. There you go. And we're going to, let's say we just do 1 decimal point, okay, which you'll see is actually not even necessary, because if you do this calculation out, what you get is that the effective spring constant for these inputted parameters is exactly 4. And maybe we should be more careful here and say, okay, what are the units, just to let us ourselves remember in case we come back to this. The units are the same units that we had for the input of this problem, so they're going to be kilonewtons per millimeter, just like that. And so now it includes the units. And let's just say that you wanted the result in something like newtons per meter, which would be a big number, but we can do that. So we'll just do MP, and this is the numeric. I can't even see. There we go, MP. And 1000 newtons is equal to 1 kilonewton, and 1,000 millimeters are equal to 1 meter. So it's actually times 1e6. Okay, so you multiply by a million. So it's going to be a big looking number. But this would give us newtons per meter, like this. Okay, like that. So this is a way to do kind of simple algebraic manipulation with symbols in Python, and then substitute appropriate values to get a numeric result that we can process with NumPy. Thank you.